So in order to draw the body plot of the system, we are going to draw or to plot two body plot. So one for magnitude and one is for the phase. Okay. So if we have like such system which consists from forward transfer function and backward transfer function. So if we apply the input for this system, which is sinusoidal waveform, as the input of the system, the output or the response of the system will have the same frequency, and the magnitude will be affected by the magnitude of the transfer function, and also the phase will be shifted due to the phase of the transfer function. And we said for the frequency response, our focus will be more on the j of j omega and h of j omega. So we are going to focus more on, or we try to convert or to change our transfer function to some specific standard form in order before going to draw the body plot. So as you can see here, there is standard form to draw for writing the j omega or g of j omega, h of j omega. Here why we have this one? So because we said this when we talk about the closed loop transfer function. So on the denominator here, we are going to have like gs here over 1 plus gs hs. For that, we are going to replace each s by using j omega here, which is more on for the frequency response calculation or for drawing the body plot. So this is the transfer function actually, or the open loop transfer function. For the forward transfer function consists from the zeros in the denominator and the numerator. Here we have zeros, 0 1, and as the first zero, the second zero, the third zero. It depends on how many zeros do we have. We have the k, which is the gain of our transfer function, like we see in chapter 5. Then in the denominator we have the poles. This is the standard form of the transfer function, forward transfer function. But in this chapter, we are going to replace each s here by using j omega. Okay, so you are going to replace s by j omega in order to solve or to study the stability of the system in the frequency using frequency response. After you replace each s by j omega and in the transfer function here, you are going to divide over the value of the zero or the value of the pole. Why? We want to see this form. This is the standard form of the transfer function to draw the body plot. In order to draw the body plot here, so we need to convert it into this form. So we are going to divide over the zeros or zero here, 0 1 0 2 0 3 and so on. So in order to get 1 here, let's see, like unity. So after j here, we have the value of the frequency over the value of the 0, the value of frequency over the value of the pool, like this one. So this is the general form or the standard form before you go to draw. After we do this one, or after we convert our transfer function into the standard form, it's easy for us to identify the value of frequency for the x domain. I mean for the x-axis. So we are going to draw the relation or the plot for both magnitude and phases with a specific value for omega here, because this will make it easier for us to calculate the value of log value. I mean like the 20 log value of this transfer function in order to draw the phase and magnitude plot, as we will see in the example later on. Okay, so but for now I want you to focus more on that we need or we have to convert the s operator here by using the j omega, and we need to leave the value here or the shift by 1 plus 1 plus 1 plus 1 plus 1 for all zeros and poles factors. In order to draw the body plot, actually usually we use the software in order to draw the body plot of our transfer function of our system. Okay, but if we want to draw this body plot by using hand, I mean by using or manually on a semi-log paper, we can split or we can divide our transfer function into some parts, and we draw it individually. For each component in our transfer function will be drawn individually. Then at the end, we are going to combine all drawings into one plot, okay, for magnitude and one plot for phase. So usually the transfer function consists from some specific or standard elements, okay. So for the KJS that we mentioned before here, we said the transfer function in this form consists from the gain and consists from first order zero, first order poles, and also if we have j omega here, it will be like integral pole. If we have j omega here, it will be integral zero, derivative zeros. So this value actually is like standard component for the transfer function. We can draw each component individually, then we combine all these drawings into one body plot for transfer function for the magnitude, one body plot for the phase, as we are going to see later on. So what are the basic factors that very frequently occurs in the arbitrary of the transfer function? So we want to define this component of factor of the transfer function. The first factor in the transfer function, we should have the gain. So the gain k here, usually always we see the value of gain. Gain is any value. It can be like, for example, if we have 2s plus 2, so or s plus 3. So the value 2 here represent the gain for our transfer function. If we have 100 over s plus 2, s plus 3, so our gain is will be 100. It's the value of the gain or the constant that exists in the numerator of our transfer function. Okay, so each transfer function has a gain. If there is no value here, it's 1, so the gain is equal to 1. So the second element or the second factor in our transfer function, it will be the integral or derivative factors. Integral or derivative factors represent the zeros or poles at the origin. When we say at the origin, means the zeros and poles at this point, at the 0 point, 0 and 0 point. So do we have poles and 0 at this point? If when we should have such pole or such zeros, if the transfer function, for example, consists from like this one, s plus 1 over s plus 2, s plus 3. So in this case, we have 1 0 at origin and we have 1 pole at origin. Okay, that means this 0 at origin, we call it the integral, I mean the derivative 0 and the integral poles. Okay, so both either integral or derivative zeros and poles here represent the value of pole at 0 at the origin. So if I ask you now what is the 0 here, the 0 will be at 0 point, correct? Z at 0 and Z at Z1 equal to 0, Z2 is equal to negative 1, for example, for this case. Or here B1 equal to 0, B2 equal to negative 2, B3 equal to negative 3. So we have 3 balls, 3 zeros, but there is 1 0 at origin, 1 ball at origin. At origin, that means the point 0 of 0. Okay, so this is the second factor or the second expected factor that exists in our transfer function. The third expected factor, which is the first order factors. So in the case of the first order factor, we are going to use this one, s plus 1. So if we have s plus 1, s plus 2, s plus 5, s plus 100, whatever is the value, that means this is first order system. For that, we call it first order factor because the highest order of s is 1. So s plus 2. So what is the power of s here? It is 1. For that, we call it the first order factor. So in this case, we may have first order 0 or first order poles. If it is exists in the numerator of transfer function, so it is a 0. If it exists in the denominator of the transfer function, so it is a pole. Okay, so after we define the three main factors here and the one that we are going to cover in the such symbol systems, maybe there is some system which has second order factors, okay, which is go to s square and so on. So our focus in this chapter, actually we are going to consider up to the first order factors here. Okay, so after you identify the main part of the transfer function, which is the gain, integral and derivative factors, and also first order factors, we are going to draw each part individually. So we are going to draw magnitude and phase for the gain, magnitude and phase for the first the integral, magnitude and phase for the derivative, magnitude and phase for the first order pool, magnitude and phase for the first order zero. After we draw all these plots, we are going to combine into one plot, which represent the body plot of our of the whole or the entire transfer function. We are going to see that in examples. But firstly, before we go to apply example to find this body plot and to draw the body plot for the system, we are going to draw the body plot for each component individually. Okay. After we learn how to find the body plot or the standard body plot for each part, we are going to combine both or all into one graph or into one plot. So how to draw the body plot here, the body plot for the gain. So if I want to draw the body plot of the gain, we said the body plot of any element consists from two parts, which is log magnitude and phase. Okay, so we should have two graphs, one for the log of magnitude and one is for the phase. When we say log magnitude, that means we are going to find the value of 20 log of the value k here. So we are talking about k, so we are going to find the value of 20 log k. What is k? K represent the number, a number constant of the gain. So for example, if it is 20 log 1, that means it will be 0. 20 log 10, so it will be 20. Okay, so it's all in dB here. Okay, so we are going to draw each element here alone as a constant number or as a line which the value with the value of 20 log in decibels. Okay, then the angle of the constant number, actually if we have number, if we said s equal to 5, for example, if I ask you now, if we assume s this is a complex number, or we want to write this s in the form of magnitude and phase, so the magnitude of s equal to 5 and the angle of s here equal to 0. Why? Because it's a real number. But if we have s equal to j5, so the magnitude of s is equal to 5 also, but the angle of s here equal to 90. This for example. Okay, so how to draw, how to represent the gain here. The gain will be constant number. Since it is a constant number, so it has a magnitude which is 20 log k, and it has the angle which will be 0 here. Why? Because all the real number has angle of 0. Whatever is the value of s here, or whatever is the value of j omega here, so of k, so the value of the angle will be equal to 0. If you have imaginary number, its angle must be 90. If you have a complex number, so its angle will be tan inverse imaginary part over real part. Okay, this is how to define or how to find the angles. So in the case of k, k is constant, so it has magnitude of 20 log k, it has angle of 0. So if we want to draw the body plot for the body plot for the gain, it will be like this one. So the magnitude bar, this is the magnitude decibels and the magnitude in decibels, and here we said the horizontal is represent the frequency in radian per second, which is like related to j omega, correct? It's in radial frequency in radian per second, for example. So here, if we want to draw the magnitude will be 20 log. If k equal to 5, for example, 20 log k will be 20 log 5, so it will be 14 dB. So when we draw the magnitude here, or the log magnitude, we go to the point of 14, we draw straight line in the semi-log paper. So this will be the body plot for the value of the gain, which is for the gain of pi. Okay, as you can see here. So if we want to draw the line, it will be like the body plot for the magnitude or log magnitude. This will be the line with the value, with one constant value, which is 14 dB. This is for the magnitude. We said the body plot has two drawing or two plots, one for magnitude, one for angle. For the angle one, it's here. We said the angle of the gain is equal to 0, so we just draw line on the 0 axis, on the on the x-axis here with 0. Okay, so this is the, excuse me, this is the body plot for the gain. In the case of the gain, which is a constant, actually gain is constant number. This is the first component or first factor. The second component will be the value of the zero or poles at the origin. So integral or derivative factors. So when we talk about the integral, we are focused on the pool. When we say derivative, we are focused on the zero. The integral is related to the denominator. Derivative is related to the numerator. Okay. So for the derivative factor here, for the derivative factor, which is related to the denominator here, numerator of the transfer function. If we have, this is the transfer function. For example, we say gs, or in our case here, j omega, because we said we are going to replace s by j omega here. If j is equal to s over s plus 1, for example, this one, it has one pole, 1 0 at origin, so it has one derivative factor, which is s, and it has one pole at -1, so this will be like the second first order. So our focus here now on the integral here. When we said integral, we are going to focus on the value of s, or the 0 at origin here, so it will be like j omega over j omega plus 1 when we convert it into the standard form. Okay, so how to draw such 0 exists in the numerator or exists in the origin point. So in order to draw this 0, we are going to apply the same formula. The magnitude for this, we have two plots, one for magnitude, one for angle. So what is the magnitude for g omega, g of j omega here? It will be 20 log omega. Okay, so 20 log omega, that means the value of omega, because we are going to draw the for frequency here, for j omega here, we are going to draw the magnitude or log magnitude, lm. Okay, so for each value of omega, we need to find the value of the log. So for example, we are going to say 20 log 0, 20 log 1, 20 log 10, 20 log 100, and so on, for different value of omega. So for example, here, if we have the value of omega change from 0.1 until 1, so this is, we call it one decade. Okay, one decade means for 10 values. So you can find here 0.1, 2, 3, 4, 5, up to 1. So you are going to find 10 values between 0.1 and 1. And usually the semi-log paper is divided in this form: 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8. But here we just omitted some value just to, but it will give you different, when we talk about the range from 0.1 to 1, it gives you 10 values in the semi-log paper, or 10 lines. Okay, for each value here, we are going to find what is the log magnitude. So 20 log 0.1, if you use your calculator to find 20 log 0.1, will give you negative 20 dB. 20 log 0.2, it will give you negative 14 dB. 20 log 0.4, it will give you negative 8 dB, and so on, until you reach to 20 log 1, so it will give you 0 dB. That means within 10 values or one decade, our value or our log magnitude changed by 20 dB. So from here 0, here 20. So it means the difference between the two value from the beginning of the decade until the end will be 20 dB. So the slope of our line for the log magnitude here will be 20 dB, or negative 20 dB, positive 20 dB. So if you want to find the slope usually equal to y2 minus y1 over x2 minus x1. So for example, here y2 in our case is 0, so it will be 0 minus negative 20, okay, over x2 minus x1, which is 1, y2 over y1 over x2, so it will be like x2, which will be 1 minus 0.1. Okay, so in this case here, if you want to find the slope will be negative or 0 minus 20, so it will be like 20 dB. The change in 20 dB here, this is 1 decade, so the change in the value of 1 decade will be 0 minus 20, so it will be positive 20 dB. So the slope of our line for the log magnitude for this value will be 20 dB per decade. Per decade means per each 10 values. Here we have 10 values from 1 to 0.1. We have 10 values, which is 0.1, 0.2, 0.3, 0.4, 0.5 until 1. So this we call it 20 dB per decade. So if we want to draw this line or for log magnitude or this plot for log magnitude, we are going to see such line. Start if when omega equal to 0.1, the dB is equal to negative 20. When omega equal to 1, the dB will equal to 0. So if we can see the table here, the previous table, it gives you this value, correct? So if you want to draw, if you want to see, I draw from 0.1 to 1 and the dB is negative 20 to 0. So you can see here, this is the line that we represent in the first decade. That means it will be increased by 20 dB per decade. This is from here to here, we call it decade. Okay, so this is 20. Now for the next also will be 20 dB per decade. So the next value start from 1 until 10, it will be also 20 dB per decade. So here we can see 0, this is 10. In front of this value here, it will be 20. Okay, then from this point to the next decade, which is 100, for example, it will be here. So it will give you here also 40 dB because each time will increase by 20 dB, 20 dB, 20 dB. So the slope of our line will be 20 dB per decade in the case of the derivative 0 or 0 at origin. For the angle for the derivative 0, since we have this one, j omega, that means if we have j5, what is the angle of j5? It will be 90 degree. So the angle of j6, it will be 90 degree. The angle of j100, it will be 90 degree. So if we want to draw the plot for the 0 at origin, it will be 90 degree positive. So this is the plot for which is 90 degree. We just come to here, draw one line at 90 degree, and this represent for all value of frequency we only have we will have the 90 degree angle. This is for the 0 at origin. In the case of the bull, actually the situation is the same. We have the slope 20, but here it will be negative because the bull, in the case of the 0 of the bull, the value will be on the denominator, not in the numerator. Instead of we have 20 log n, we will have negative 20 log 1 over n, because actually if you have 20 log 5 must equal negative 20 log 1 over 5. This you just try by using your calculator, you will find this formula is the formula of log is correct. When we have the value of n, it will negative 20 log of the value of 1 over n. So in the case of n, we got 20 dB per decade. Here we are going to have negative 20 dB per decade. It is the same value. And the angle for this case, if you have the value of j omega equal to j5, negative j5. If you have negative j5, that means it is the same as if you have j over 5. Sorry, if you have j omega here equal to 1 over j5, it will equal to the j here will go to the up, so it will be negative j. So if you have negative j here, the angle of the negative j will be negative 90. Okay, 1 over j, if you want to take it up, it will equal to 1 negative j. So if you take j up here for the operator for the imaginary number, you are going to get negative j. If you got negative j here, negative j means the angle of negative 90 degree. So in the case of the pole at the origin, the drawing or the plot here will be negative 20 dB per decade. That means we start from 20. After one decade, which is here, we are going to reach to 0. So here, from this point to per one decade, we have negative 20 dB. Then from this point to the next decade here, which is here 10, so we have negative 20 dB again. Then it will decrement, okay, decrement by negative 20 dB. So when we reach to 100, the frequency of 100 hertz, for example, or 100 radian per second, you are going to have negative 60 dB per decade. Okay. So this is how to draw the magnitude. For the angle, we said just you need to draw negative 90 degree. Okay, in the case of the 0, we draw positive 90. In the case of the pole, we draw negative 90. This is in the case that you have factor at the origin, either derivative or integral pole and zeros. The third factor, which is the you have a first order factor, and in the case of the first order factor, this it's like this one. If you have s plus 2, for example, over s plus 3, s plus 5, and so on. So this we call it all first order factors. So the first order factor, that means you have a pole or 0, but it's not at the origin. It is not at this point. It can be here, it can be there, it can be at this point, at that point, but it cannot be at the 0 point. Okay, so it's not integral, it's not derivative. In this case, we are going to apply the formula for the magnitude, which is 20 log 1 plus j omega over omega 1 according to the standard form. We said in the standard form, we should have j omega over omega 1, for example, or j omega over z1 over p1 and so on. So in this case, we have j omega over omega 1, and in order to find the magnitude, we need to consider multiple values. So the main element here, we have two situations for the magnitude case, and we have three situations for the phase case. If we want to draw the log magnitude, so we need to consider this formula 20 log 1 plus omega over omega 1. So for all frequency which is too much less than omega 1, that means if I have this is the graph here, and they have this is the frequency of omega 1, okay, the value of the 0, for example, in the case of the 0, or the value of the ball in the case of the ball. So if this one is omega 1, for the frequency which is less than omega 1, that means omega will be less than omega 1. So if this value is too less than omega 1, this part will be ignored, okay, because this is value is smaller than this omega 1. So the result, if you have, for example, 0.0005 over 0.1, okay, and you make it square, you are going to get very point, or maybe very small value. So this value can be ignored. Then you have 20 log 1. 20 log 1 will give you 0, okay, so the magnitude in this case will be 0. So for all frequency less than omega 1, the magnitude will be 0. The log magnitude will be 0. The log magnitude will be 0. After, for the value which is omega greater than omega 1, so in this case we are going to find this relation 20 log omega over omega 1. So we substitute for the value of omega. If omega equal to omega 1, it will be, I mean, like omega 1 over omega 1, so it will be 20 log 1. At this point it will be 0, okay. Then after that, if we said 10 omega over omega 1, I mean 10 omega 1 over omega 1, so it will be like log 10, so it will be 20 dB per decade. Then I mean after that, if we have 100 omega 1 over omega 1, so it will be 40 dB per decade, and so on. So I mean the omega 1 here is changeable frequency, or change point for the frequency, or for the log magnitude for the 0, or also for the ball. In the case of the ball, it will be negative, so it will be go down in this case. So you can see here, this is for the case of the magnitude, and this for the case of the angle. The angle here also will have 3 points for change, which is the first point at omega equal to omega 1. I mean point omega 1 over 10, and at 10 omega 1. So these are the 2 points for change for our angle. In the case of omega equal to omega 1, so if we assume omega equal to 0, tan inverse 0 over omega 1 will give you 0. If omega equal to omega 1, so tan inverse omega 1 over omega 1, so it will give you 1. Tan inverse 1, which is 45. Then if omega is go to infinity here, so tan inverse infinity will be 90. So if we draw the plot for the angle here, we have one point, we call it omega 1 over 10, or then we have the value of 10 omega 1. In between them, before is 0, after that is here is 45, then after that will be 90. This is 90, here is 45 per decade, and here we have 0 values. So you can see here, this is how we draw the magnitude, which is, we said at the omega equal to omega 1, we have changed from 0 to 20 dB per decade or 6 dB per octet. So in the case of the 0 here, actually, our focus on the 0. Then for the angle also, it will be from 0 to the change point will be we have two changeable point, which is omega 1 over 10, and the next changeable point will be 10 omega 1. So this is how to represent the angle. So the first will be 0, then we have 45, then we have 90 degrees. This is for the case of the 0. For the case of the pole will be the same, but the angle will be different. So the magnitude here will be negative instead of, the magnitude will be represented by 0 until omega 1. Then it will go negative 20 dB per decade. For the angle, it will be 0 until omega 1 over 10 or 0.1 omega 1. Then it will be 45 until 10 omega 1, then it will be 90 for the rest until infinity. Okay, so you can see here that how to represent the same 0, negative 45, and negative 90 here. In the case of the angle, it will be negative 90. Sorry, this one is negative actually, not positive, so it will be like this one, 45 and negative 90. So just remove this, because when we talk about the ball, the values all will be reversed and will take the negative sign. But when we talk about the 0, all the values will be positive. So here for the ball, it will be zeros. It will be negative values, either for the magnitude or also for the angle. As you can see here, negative 45, negative 90. But in the case of the zeros, all are positive. So here we have positive 45, positive 90, and here also we have 20 log for which is positive here. Okay, this is how we draw the different components for the transfer function or the different factors individually. So we draw for the gain, we draw for the zero and bull at the origin, we draw for the zero and bull for first order factors. Okay, after you draw for each component of your transfer function, you can go to combine all into one graph, actually, or one plot for magnitude, one plot for phase. We are going to see these things all in, or we apply these steps by using example. But before we go to the example, we want to know, or want to summarize all this situation in this table. We have two table here to summarize the factor and the magnitude and the phase drawn. So for the factor K here, we said the magnitude is 20 log K, whatever is the value of K, then the phase here, the phase will be 0. This is for the gain, whatever is the value of the gain. The gain can be, the gain can be changed for any positive numbers. Okay, so the angle is 0, the gain is 20 log, whatever is the value, so it will be changed. Then for the 0 at origin, or for derivative 0, so the angle here, or the magnitude will be 20 dB per decade, increment of 20 dB per decade per each 10 values. The slope will increase by 20 dB, and the angle will be positive 90. For the pool at the origin, which is the integral pool, in this case, that the slope of the magnitude will be negative 20 dB per decade. It will be negative here for the pool case, and the angle will be negative 90. For the first order factor here, which is the for the zero first order factor, the we have one change point for frequency, which is at the 0 point here. Before the zero value, all the magnitude will be zero. After the 0 point here, we have the slope of 20 dB per decade positive. Here, before the bull until before the bull value, or the magnitude is equal to zero, log magnitude equal to zero. After the bull value, the magnitude will be negative 20 dB per day. The angle here before the z over 10, that means 0.1 z, you are going to multiply your 0 by 0.1 or divide it by 10. Before it will be 0 angle. Between 0.1 z and 10 z here, the slope will be 45 degree per decade. 45 degree per decade. After the 10z, it will be 90. The same here, before b over 10, it will be 0. Between b over 10 and 10b, and b here represent the point, the value of the pole, z represent the value of the 0. Okay, so it will be negative 20 dB, 45 angle, or 35 degree per decade. Then after the 10b, it will be negative 90 degree. So the two cases here we do not consider, because it's more related to the second order system. Our consideration for the first order system. All these values also are summarized in this table, the same here again, but it's more clearer according to the textbook that we used. So it show for the k value, for the zero at origin, and also for the zero bull at origin here, and for first order bull, and I mean zero at origin and zero first order zero, bull at origin and first order bull. Okay, so next video we are going to have one example to draw the all component, then we combine all component in one plot for log magnitude and one plot for the phase.